Okay, so we're here with part 2 of the review. We're beginning in chapter 25. Last time we covered 4 chapters, 21 through 24. We were able to do 2 questions in our 3-hour review session. That's a little bit slow. We won't be able to get through all the chapters today if we don't pick up the pace a little bit. So here's what we're going to do. We're going to do a conceptual question from each of the chapters. So we're just going to go chapter 25, then chapter 26, and so on until we hit chapter 31. Then we'll go back with the time we have left, and we'll fill in like a second question from each of those chapters. Okay, so first question is coming now. I'll just pause the video and be back when everything is there. All right, we're back. This is our first question from chapter 25, all about current, resistance, and things like that. Okay, so the figure shows a steady electric current passing through a wire with a narrow region. What happens to the drift velocity of the moving charges as they go from region A to region B and then to region C? So in the figure you can see here in region A, we have a wire with a wide diameter, and that diameter decreases as we go into region B. And then from region B back to region C, the diameter increases again back to the original diameter. Okay, our options here are the drift velocity decreases from A to B and increases from B to C. The drift velocity increases all the time. The drift velocity remains constant. The drift velocity decreases all the time. The drift velocity increases from A to B and decreases from B to C. So if you're watching the recording, pause the video now, try this question yourself. The rest of us, we're going to think about this one individually at first, and I'll take your answers and pair you up into groups to see, to try and convince your neighbors, to convince your partners that your answer is correct, and then I'll check your guys' answers again after that. Same style as last time. Okay, so pause the video if you're watching on YouTube. Okay, for this question here, there's basically unanimous consent here that the answer should be answer E. The drift velocity increases from A to B and decreases from B to C. This is the correct choice. As the diameter of the wire decreases as we go from A to B, the resistance in the wire goes down, right? Goes up. The resistance in the wire goes up, which seems to imply that the current would go down, right? That can't be the case though, because we have Kirchhoff's current law. So the current I has to be the same in those 3 regions. Therefore, the drift velocity must increase. The speed of those electrons, the average speed of those electrons in that wire has to increase to maintain a constant current. Okay, so the resistance, let's put it in kind of like a little bit equation. So the resistance goes down. So in order to make the current go up, the drift velocity has to go up. Okay, because resistance going down seems to imply the current is going down. We can't have that because we have Kirchhoff's current law. Okay, Kirchhoff's current law, current remains the same in the wire. Okay, we'll be back with remains the same with the next question here in just a second. Remains the same in each segment. Okay, question from chapter 26 now. As more resistors are added in parallel across a constant voltage source, the power supplied by the source increases, decreases, or does not change. So pause the video now if you're watching the recording and think about this one, and we'll be back with the discussion in just a moment. All right, we're back, and after we had some disagreement in the first round, but after some discussion here, we all were able to settle here on the power supplied by the source increases, which is the correct answer. The thing to remember here is that the power supplied by the source is the current through the source times its potential difference. So if you increase the current, you will increase the power delivered. Or if you decrease the current, you will decrease the power delivered. And adding resistors in parallel, you have to remember that 1 over Req equals 1 over R1 plus dot, 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 all the way out to however many resistors you have here. And when you combine these resistors in parallel, you're decreasing the equivalent resistance here. Req will always be lower than the lowest resistance value that you have connected in parallel. Okay, so we'll be back with the next question in just a moment. Okay, so we had a question about how the current is actually affected by adding in these resistors. The answer to that is simply draw yourself an equivalent circuit where the only resistor that you have there is the combination of all the resistors, which is Req. And Req is less than all of the resistors that are connected in parallel. And so if I want to know what the current is in the circuit, I just apply Ohm's law. So delta V over Req here. And since Req is smaller the more resistors you connect in parallel, then the current must be increasing because Req is dividing. Okay, so you divide by a smaller and smaller number, you're going to increase the current. Okay, we'll be back with the next question in just a second. Okay, we're here with our question for chapter 27 now. A vertical wire carries a current vertically upward in a region where the magnetic field vector points toward the north. What is the direction of the magnetic force on this current due to the field? Downward, toward the north, toward the south, toward the east, or toward the west? Just to add some clarity to this question here, you have to imagine you have your coordinate axes here, north, west, east, and south, and into, with an X here and a circle around it, this is down. So that would be like towards the center of Earth, right, into the ground. And we have upward here is that dot with a circle around it. So that'd be like out towards outer space, away from Earth. Okay, so go ahead and think about this one yourselves to begin. Pause the video now if you're watching on YouTube. We'll be back in just a second with the discussion and answer. Okay, so after some discussion, we've all settled on toward the west, which is the correct answer here. So the wire is carrying a current upward. That means that the current is in this direction here. And we're being told that the magnetic field is pointing in the north direction. So that's a magnetic field in that direction. So we need to take our fingers and make our fingers point away from our screens and curl upward. And we can see that our thumb points to the left of our screen. You must be using your right hand, and my thumb is pointing to my left right now. So it might appear like it's pointing to the right to you, but for me, it's pointing to the left. So we get that the magnetic force, we always draw forces in red, right? The magnetic force here is due west. So E is the correct answer. All right, we'll be back with the next question in just a second. All right, we're back with a question out of chapter 28. A vertical wire carries a current straight down. To the east of this wire, the magnetic field points blank. Again, when the problem says that it points straight down, that means that it is going into the page, and we have north, west, south, and east here like this, okay? And then coming up out would be up. All right, so take some time to think about that one on your own. Pause the video now if you're watching on YouTube and give this one a shot yourself. We'll be back in just a second with the discussion. All right, well, we're back, and it seems like in round one, we have pretty much unanimous agreement here that the answer is D, towards the south. What we want to do here is we want to stick our thumbs in the direction of into the screen. So stick your thumb in the direction into the screen here. So this is my right hand that I'm using. I'm sticking my right hand's thumb in towards the screen, and I curl my fingers around, and my fingers are curling in the direction of the magnetic field. So if I do that here for my screen, I see that on the east side of the current, my fingers are pointing down. So my fingers are wrapping around like this. And so on the east side here, so this is the east side, it is pointing downward to the south. So that would be this way. So this is south. Okay, so magnetic field pointing towards the south. All right, we'll be back in just a second with the next question in chapter 29. All right, we're here with a question out of chapter 29 now. A circular loop of wire lies in the plane of the paper. An increasing magnetic field points out of the paper. What is the direction of the induced current in the loop? A, counterclockwise, then clockwise. B, clockwise, then counterclockwise. C, clockwise. D, counterclockwise. And E, there is no current induced in the loop. So take some time to think about that one on your own. Pause the video now if you're watching on YouTube. Give this one a shot. We'll be back in just a moment. All right, we're back. So we have a majority for answer C, clockwise, and a few people are answering counterclockwise. Let's try to understand which one is the correct answer here. A circular loop of wire lies in the plane of the paper. An increasing magnetic field points out of the paper. So there's an increasing magnetic field here, B. So it's increasing. That means the magnetic flux in this loop is increasing, right? So once we've identified how the magnetic field is changing, we need to go against that change, right? So the induced magnetic field is going to go into the page because this magnetic field is increasing out of the page. Okay, so our induced magnetic field, I'll do it in green, is going to be into, so be induced. And since that's the case, we can use right hand rule to get that the current is actually going around in this direction here. So this is the I induced here. And correct me if I'm wrong, but this is 1, 2, 3 o'clock, 4. This is clockwise, right? So the answer here is C, clockwise. Okay, so we'll be back with the next question in just a moment. Okay, this is our first question in chapter 30 now. Which of the following statements about inductors are correct? There may be, there may be more than one correct choice. I actually like these questions because you always get a lot more discussion on these ones where there may be more than one correct choice. Okay, so A, when it is connected in a circuit, an inductor always resists having current flow through it. B, inductors store energy by building up charge. C, when an inductor and a resistor are connected in series with a DC battery, the current in the circuit is reduced to 0 in one time constant. D, an inductor always resists change in the current through it. E, when an inductor and a resistor are connected in series with a DC battery, the current in the circuit is 0 after a long time, after a very long time. Okay, so if you're watching on YouTube, pause the video now, evaluate whether each of these statements are correct or incorrect, and your answer is all of the statements that you believe to be correct. We'll be back in just a moment to discuss each of these. All right, we're back, and let's take a look at each of these statements here. Just some notes here. A lot of people thought B was correct and E was correct, but most people thought that D was correct. So almost everybody chose D, some people mixing it in with B and E as well. Okay, so let's evaluate statement A here. When it is connected in a circuit, an inductor always resists having current flow through it. That's what resistors do, not what inductors do. Inductors have zero resistance. So inductors are simply wires, right? And we always treat wires as having negligible resistance, or R equals 0. So this one is not correct. Inductors do not resist the flow of current. Just as an example, I can have 10 amps of current flowing through an inductor indefinitely, right? Just the 10 amps continues to flow through the inductor, and the inductor never dissipates any of that, any energy, or never supplies energy even, as long as that current is steady. As soon as the current starts to change, though, then that changes everything. B, inductors store energy by building up charge. This is an interesting choice. Inductors do not store energy by building up charge. That's what capacitors do. Inductors can store energy in the magnetic field. So if I have an inductor, like this, the way that that inductor is going to store energy is the magnetic field lines that emanate around the inductor. And so maybe the magnetic field is doing something like this. And in this case, then that inductor could have some energy stored there in the magnetic field. Just to give an equation to this, the energy density stored in the magnetic field is 1 over 2 mu 0 b squared, right? And how do capacitors store energy? We like to talk about capacitors store energy as charge on the plates, which is kind of an okay way of thinking about it. But really the way you should think about it is that the energy is stored in the electric field between the plates of the capacitor. So, and that energy density is 1/2 epsilon naught magnitude of the electric field squared. Okay. So answer B here is not correct. I don't think anybody went for C in round 2, but let's think about it. So when an inductor and a resistor are connected in series with a DC battery, the current in the circuit is reduced to 0 in one time constant. Again, this to me sounds like a statement about an RC circuit, a circuit with a capacitor, right? But even if there was a capacitor in a circuit, the current wouldn't reach 0 in one time constant. The general rule for that, for all practical purposes, for all engineering purposes and so forth, it's 5 time constants. Okay, in 5 time constants, something like 99.98% of the current has vanished. So for all practical purposes, that's roughly 0, right? For real circuits. Okay, so C is incorrect here. What happens in an inductive circuit and an RL circuit is the current actually increases to a certain value and then it stays at that value. It doesn't go from some value down to 0. It goes from 0 up to some value and remains at that value. Okay, D was pretty popular here. An inductor always resists any change in the current through it. I would agree with this. And the way it resists is by Faraday's law, right? So Faraday's law is minus L di dt, right? So any change in current there over time is resisted by the inductor, and the resistance is due to that minus sign there. So the induced voltage E is opposite the change in current by that minus sign in the equation. And L, of course, there is simply the inductance of that inductor. So it's how good of an inductor it is. Bigger L means better inductor. So D is correct here. So maybe we give this one a blue check mark. Or maybe I should go green check mark, huh? Okay, and E, when an inductor and a resistor are connected in series with a DC battery, the current in the circuit is zero after a very long time. We already talked about this, so to me this sounds like a capacitor and a resistor connected in series. So after a long time, the capacitor would build up charge on the plates and then there would be zero current. For an inductor, after a long time, though, the current just it reaches a steady state. The current will just remain constant, but not zero, because an inductor does not block current flow in any way. So as soon as you reach that steady state current, it's like the inductor is not there at all. So E is incorrect. We do have a chat here. Okay, that's not a question. All right, so we'll be back with the next question from chapter 31 in just a moment. All right, so we're back with our question out of chapter 31. This is our last conceptual question, and you could think of it that way, but even calculation problems require a little bit of conceptual knowledge. But once we're done with this question, we'll start going back through each of the chapters we've already gone through, and we'll do a calculation type problem. So we'll need our calculators and maybe some formulas that will be provided for us. Okay, so this question, which one of the phasor diagrams shown below best represents a series LRC circuit driven at resonance? Okay, so we have a couple choices here. I can just describe them a little bit. So choice 1 here, the voltage on the inductor is bigger than the voltage on the capacitor. In 2, the voltage on the capacitor is bigger than the voltage on the inductor. In 3 here, we have that the voltage on the inductor and the voltage on the capacitor are the same. In 4, we have and in options 1, 2, and 3, the phase angle between the inductive voltage and the capacitive voltage is 180 degrees. Here in option 4, it looks like the voltage on the inductor and the voltage on the capacitor is the same, but they are out of phase by 240 degrees. Excuse me, 120 degrees. Probably should take the smaller of those angles. And then in option 5 here, it looks like the voltage on the inductor and capacitor are the same. But when I say the same, I mean the magnitude of those phasors is the same, by the way. Maybe I was a little bit unclear on that. But they're almost in phase. So the voltage on the inductor, the voltage on the capacitor, the phase angle between those two is very close to zero, but not zero. Okay, and in each of these schematics here, the voltage on the resistor seems to be roughly always in the same direction, but it looks like in options 4 and 5, the voltage on the resistor is slightly larger in magnitude, whereas in options 1, 2, and 3, it's slightly smaller in magnitude. So I'll let you guys think about that. Think about the different pictures here and try to determine which of these constitutes resonance in the RLC series circuit. We'll be back in just a moment with a discussion on the answer here. Okay, so we're back with this question, and it looks like we're unanimous. We all agree that the answer is 3 here. We need the sum of VL plus VC, or rather, we're used to writing it as VL minus VC equals 0. If you write VL and VC as complex numbers, which is what they are, then you would add the 2 and get 0. As you can just see from the diagram there. But we need VL minus VC to be 0, and we need them to be 180 degrees out of phase. So, and 180 degrees out of phase. Again, so that way when we add them as complex numbers, we get 0. Okay, so that will give us resonance there. There's probably some other ways to think about why that diagram is in resonance, but that's kind of like what I would think about. Um, so yeah, we'll go ahead and get ready for calculation type problems now. So the next question that I throw up will be calculation based. So get your calculator ready. Maybe grab your notes, look at some formulas, review, get a collection of some formulas for yourself. I'll kind of put some formulas up with those questions as we need them. So we'll be back with the next question here in a second. All right, we're here with our first calculation question out of chapter 25. The diameter of a 12 gauge, copper wire is 0.081 inches. The maximum safe current it can carry in order to prevent fire danger in building construction is 20 amps. At this current, what is the drift velocity of the electrons? The number of electron carriers in 1 cubic centimeter of copper is 8.5 times 10 to the 22. And the fundamental charge unit E is 1.60 times 10 to the negative 19 coulombs. For our answers here, we have 0.044 millimeters per second, 0.44 millimeters per second, 0.44 centimeters per second, 0.44 meters per second, and 4.4 centimeters per second. Okay. So a couple things we're going to need for this question that would be provided on the formula sheet if I gave you a question similar to this one. Typically, I won't ask you to make conversions on many problems. So 1 inch is 2.54 centimeters by definition. So this right here is a definition, which means that both sides of this equation have an infinite number of significant figures. You may also want to know how to find the resistance of a wire, right? The resistance of a wire depends on the material, it depends on the length, and it depends on the cross-sectional area of the wire. So if my material is copper versus silver, there's a different resistivity there. So that will change the overall resistance of the wire. If my wire is longer, that increases the resistance. There's more atoms that the electrons need to collide into and so forth on their arduous journey through the wire. Actually, that was probably a bad explanation. And then there's the cross-sectional area. So if you make the wire thicker, it's easier for the electrons to get through the wire. Okay, is there anything else that we might... Drift velocity. So what's the connection between current and drift velocity? So the connection between current and drift velocity is the following. So the density of charge carriers times the charge of those charge carriers, which would be E in magnitude, times the drift velocity times the cross-sectional area of the wire. Okay. So this part right here is J, current density. If you multiply J by the cross-sectional area of a wire, as long as that cross-sectional area is constant, you get the current I. I believe these are all the formulas you would need to be able to tackle this question. So we're going to pause the video now and give it a shot yourself if you're watching the recording on YouTube. Those of you who are here, I'll give you some time to work on this one. We'll be back in a minute to discuss the answer. It looks like we are all in agreement that the answer should be answer B here, 0.44 millimeters per second. Okay, let's try to get there with it. The first thing we need to do is to get the get the, what are we looking for again? Sorry, I forgot. At this current, what is the drift velocity of the electrons, right? So we can solve for the drift velocity to see what we're looking for here. So the drift velocity is the current over the charge carrier density times the charge of those charges divided by the area here. Okay, and so it looks like we have everything here except for the area of the wire, but we're given the gauge of the wire, right? So since we're given the gauge of the wire, gauge is 0.081 inches. We need to convert this to centimeters. So we need 2.54 centimeters per 1 inch. The reason we need to convert this to centimeters is because we're given the number of electron carriers in 1 cubic centimeter of copper. So this is our charge carrier density, which has units of centimeters, excuse me, centimeters cubed in the denominator. Okay, so our N there has units of centimeters inverse cube. Okay, so we get this answer in centimeters there. Then we can calculate the area of the wire there. Okay, how would we calculate the area? Well, the cross-sectional area of a wire is pi r squared. And so our area will have units of centimeters squared, which is fine because, again, the charge carrier density has units of inverse centimeters cubed. Okay, that will ultimately leave us with 1 centimeter left over for our units. And so when we go to calculate our final numerical result, the units will be centimeters per second. Okay. And so we'll have to look at these answers here. So that does not necessarily mean the answer is C or E. The answer might be A, B, or D, just depending on the order of magnitude that we get for that. Okay, so I'm just going to kind of approximate what this might look like here. So, for our current, we have 20 amps. For N, we have this 8.5 times 10 to the 22, right? For the charge of the fundamental charge unit here, we have the 1.6 times 10 to the minus 19 coulombs, right? Leaving the units off here. And then for the area, we simply plug in whatever we get for this here, plug it in here for R, and then take this pi r squared and plug it in over here. And you will indeed get answer B. Okay, so you need to calculate that yourself and make sure that you can get that answer there. We'll go ahead and pause now, and we'll be back with the next question in just a second. All right, we're back with a calculation question out of chapter 26. 13 resistors are connected across points A and B as shown in the figure. If all the resistors are accurate to 2 significant figures, what is the equivalent resistance between points A and B? So we have a circuit diagram here in this figure. A lot of 2 ohm resistors here on the top and on the bottom, and we have a couple 6 ohm resistors in between, and then we have this 4 ohm resistor all the way on the end. Okay, so we'll have to think about how to combine these resistors to figure out what the equivalent resistance is between points A and B, right? Our options here are 4 ohms, 6 ohms, 8 ohms, 10 ohms, and 12 ohms. So it looks like our final answer is going to be a nice round number. So you might suspect that as you're going through this question, that the numbers at every stage are going to be fairly decent. They're going to be, maybe a nice fraction, maybe even a whole number. But if you start to, like for example, if I look at this circuit, I see a lot of even numbers, okay? So if I'm going through my calculations and all of a sudden I get an odd number, right? I know I've done something wrong, right? Because you add up even numbers, you get an even number. You multiply even numbers, you get an even number, right? An even number divided by an even number is an even number. So at any stage of the game here, if you end up with a 7 or a 9 or something, a 13, you know you've made a mistake, okay? All right, I'll give you some time to work on that. If you're watching the video, pause the video now and give this one a shot yourself. Since we will have formulas available on the final exam, I'll remind you that the equivalent resistance for resistors in series is the sum of the resistors, and the equivalent resistance for resistors in parallel is the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the resistances, like that. And special case, if you have exactly two if you have the reciprocals formula for just two things, then you can always write it as a product over sum formula, like so, okay? And these two would be for parallel, and this one would be for series. Okay, so go ahead now, pause the video, and see if you can come up with an answer on that one. All right, we're back, and it looks like everyone likes the answer C here, 8 ohms. Let's quickly see what's going on here. The way to start these problems is not to make the mistake of, for example, combining everything up here at the top or everything down here at the bottom as series. They look like they're in series, but you have to remember that the current can split here. It can go down and it can go straight across. And so those really aren't connected in series. The best way to approach these problems is to find an area where you have multiple resistors sharing the same current or sharing the same voltage. In this case, none of the resistors, as shown in the diagram, share the same voltage. So we have to look now for where they share the same current. For example, these two resistors share the same current, so we could combine those into a 4 ohm resistor. And these two here also share the same current. The current would maybe flow in that direction if the voltage polarity was like this. So these two would be a 4 ohm. Again, I see right here we have a 4 ohm, and on the bottom here we have a 4 ohm. Okay, and now it looks like this current is actually shared here. So we have these two 2s, this 4 here on the right, and these two 2s here. So it's a 4 plus a 4 plus a 4 is 12. So we have a 12 ohm resistor here for these 5 resistors. Now that's going to be in parallel with this 6 ohm resistor, right? Because if I label this, let's call this little a and little b, the voltage across the 6 ohm resistor is VAB, and the voltage across this 12 ohm equivalent resistor over here on the right would also be VAB. They're sharing the same two nodes. So we can combine these as a 6 and a 12 in parallel. Let's use the product over sum formula over here, because that's going to be the quickest way to get that answer. 6 times 12 over 6 plus 12. That's going to give us 72 over 18. And that's going to give us, I believe that's a 4, right? Because 4 times 1 is 40, 4 times 8 is 32. So we've got 72 there. So 4 ohms there. And then once we've established that that blue bubble there is going to just be a 4 ohm resistor, we can see that now the situation repeats itself again. we have these 3 4-ohm resistors here in red. So that's going to combine and give us a 12-ohm resistor. Okay, and then we have a 12-ohm resistor in parallel with a 6-ohm resistor again, and that's going to give us 4 ohms. So all of that there is going to be 4 ohms. And then we have a 2, a 4, and a 2, which are going to be in series. That's going to give us 8 ohms in total. So the equivalent resistance here between these two is 8 ohms for REQ. So that would be the correct answer, C, 8 ohms. We'll be back with the next question in just a second here. Okay, so I kind of posed the question, what would happen if we kind of threw some resistors in here kind of at a slant, at a diagonal? How would that change the problem? So I decided I'll go over this myself to save a little bit of time here during the review session. So what's changed is now these 2 ohm resistors down here, they still become a 4 ohm resistor. These two up here still become a 4 ohm resistor. But now only these two are in series. So those two would become an 8 ohm resistor. And this 6 ohm resistor here is now in parallel with this 8 ohm resistor. So let me go ahead and circle them in purple here. So this 6 ohm resistor is now in parallel. So it's a 6 ohm in parallel with an 8 ohm. So that's going to be 6 times 8 over 6 plus 8, right? Whatever that equals. 48 over 14. We could reduce this to 24 over 7, but you see it doesn't reduce to a nice neat fraction, right? So 24 over 7 there. So what that does then is I can replace all of this here. I can replace all of this here with a 24 over 7 ohm resistor, like that, okay? This one down here is a 4 still, so this 24 over 7 plus this 4 ohm resistor, those guys are in series, right? So this one plus these two here, so 24 over 7 plus 28 over 7, that's going to give us 52 over 7, and we just barely missed... Oh, no, wait, sorry, 15 over 17. 51 over 17 reduces, not 51 over 7. So actually, it doesn't matter. It's not going to reduce. So 52 over 7, we can't reduce that. Units of ohms there. And then this 52 over 7 is going to be in parallel with this 2 ohm resistor now. So we need to do 52 over 7 times 2 divided by 52 over 7 plus 2. And now you got to put your arithmetic skills to work here. Best way to do this is to carry this 7 down into the denominator. So that way we end up with 104 over 52 plus 14, which is 66. So 104 ohms over 66 ohms. Again, this can be reduced to 52 over 33, but then it can't be reduced any further. And now that resistor there is the same as if we replaced all of those with this 52 over 33 ohms. That is all I'm going to show, okay? Now you've seen it again, how to do these diagonal cases here. You just need to be a little bit more careful about it. So watch the recording again if you need to, if that was a little bit unclear, to really get a grasp on why those were in parallel, why those were in series, etc. And we're going to go ahead and move on to chapter 27 next. All right, we're here with a question out of chapter 27 now. The figure shows a velocity selector that can be used to measure the speed of a charged particle. A beam of particles is directed along the axis of the instrument. A parallel plate capacitor sets up an electric field E, which is oriented perpendicular to a uniform magnetic field B. If the plates are separated by 2 millimeters, and the value of the magnetic field is 0.60 Tesla, what voltage between the plates will allow particles of speed 5 times 10 to the 5th meters per second to pass straight through without deflection? So our options here are 600 volts, 1900 volts, 3800 volts, 190 volts, and 94 volts. Couple of relevant equations here for this particular problem. So I see something about velocity selector. I remember for a velocity selector, magnetic force and electric force should be the same, right? Magnetic force is QVB, maybe there's a sine theta. Electric force is QE, right? In this case, the magnetic force and electric force by design are going to be anti-parallel. They're going to be on the same axis. And the magnetic field and electric field are perpendicular to each other and perpendicular to the velocity of the particle. Anything else to remember about this question here? You probably also want to remember probably also maybe I see parallel plate capacitor sets up an electric field. Maybe you need to know the energy of the particles, their kinetic energy, right? If they're accelerated through a potential of QV, then they're going to have 1/2 mv squared for their velocity, right? Whoops, probably let's get rid of the K there. That's probably pretty good there for, or maybe also, excuse me, let me actually write this E here as energy because we have electric field and energy here in the same problem, being possibly relevant to the problem here. So energy is this, and then we also have, so this one right here is potential energy, and then this one over here, it's going to become kinetic energy. So this is actually energy conservation here. And then what was the other one I was going to, oh yeah, so voltage equals E times D, right? So let me write that properly. So E times D, right? So the voltage between the plates of a parallel plate capacitor is the electric field magnitude times this separation distance. Okay, that should be enough to tackle this question here. So I'll leave it to you guys now. Pause the video and try this one yourself. We'll be back shortly with the discussion. Okay, so without any discussion, we've all kind of came to agreement that the answer should be this 600 volts here, answer A. So let's just kind of go through it quickly here. If the plates are separated by 2 millimeters and the value of the magnetic field is 0.60 Tesla, what voltage between the plates will allow particles of speed 5 times 10 to the 5th meters per second to pass straight through without deflection? Okay, so we need to know how much energy these particles will have. We need to know that the, so we need to know that there's no deflection on these particles, which means this right here. So the magnetic force is equal to the electric force. And of course, the electric force being equal to the magnetic force means we have QVB equals Q times E. We can cancel the charges on both sides here. And we're being asked about voltage. So since we're being asked about the voltage, we can determine that based on the electric field that these particles are accelerated through. So particles that are accelerated through the electric field of strength E, well, the potential difference between those plates is given by this equation right here. Let me go back to red again. So the voltage is the uniform magnetic field magnitude between two parallel plate capacitors times the separation distance. And so we simply need to solve for the voltage that corresponds to that speed there. And I believe there's another formula that you can use perhaps to get the voltage in one go, but perhaps that formula is a little bit more complicated one. I probably wouldn't put on the formula sheet. Okay, so let's start a little bit of calculation here. So we're told the magnitude of B, but we don't know the magnitude of E. So we should solve for the magnitude of E. Well, it's already solved for. E equals VB. Okay. And in order to get the voltage here, if we know the velocity here, and we know the magnetic field again, so we know the electric field now. And in order to get the voltage, yeah, we can just go, I mean, this actually is this equation, this example is just too easy, isn't it? Did anybody have any trouble with this one? And then actually, did we even need to know that oh yeah, we do because of this formula right here. Okay, so plug everything in, right? This one was a little bit too easy. So it's throwing me for a loop. It's a little bit too easy. So 5 times 10 to the 5th meters per second times 0.60 Tesla, and then times 2 millimeters. So 2 times 10 to the minus 3 meters there. And let's see, just looking at it here, 6, the 0.6 times the 2 is going to give you a 1.2. Right, a 1.2 times a 5 is going to give you like a 6, right? So it looks like this one's going to work out here. So 10 to the 5th times the 10 to the minus 3, that's going to give you a 10 to the 2. So our answer there is going to be 600. Okay, that one was maybe a little bit too simple. Okay, any questions about that one? Go ahead and pause the video and we'll be back with the next question in just a second. All right, chapter 28. A long straight wire with 3 amps of current flowing through it produces magnetic field strength 1.0 Tesla at its surface. If the wire has a radius r, where within the wire is the field strength equal to 36% of the field strength at the surface of the wire? Assume that the current density is uniform throughout the wire. Okay, and you're given the constant mu naught there. Of course, that'll be given to you on the test, right? So go ahead and pause the video, try this one yourselves, and we'll be back in just a moment with the explanation. Actually, I probably should give you any relevant formulas here that you might encounter on the formula sheet, and that would be Ampere's law, right? Ampere's law is the integral of the magnetic field over some closed loop. And Ampere's law says that that integral will be equal to I enclosed by that loop times this magnetic constant mu 0. Okay, and that's pretty much all you need to tackle this problem. All right, see you in a bit. Okay, so we're back, pretty much unanimously agreeing that the answer here should be answer A. Recall that when we have a uniform current in a wire, that the magnetic field will be proportional to R. But let's go ahead and show that with Ampere's law, just so we have it here in the video. So when you have a uniform current flowing in a wire, you want to choose a circle for your path inside the wire. It looks like this. Here's our wire, like this. And we want to choose a path like this inside the wire. And then we want to orient our path like this so that it's in the same direction that the magnetic field would be in. Right, so the magnetic field there will be that way. The magnetic field over here will be this way. Right, if the current is coming out this way. And maybe I should say, in fact, that this is the current J, not the current I, because we do need to integrate this thing. So our integral on the left-hand side becomes magnetic field dot product with dl, but dl and the magnetic field are in the same direction, and dl parameterizes a circle, so the circumference of that circle is going to be 2 pi r. So ultimately we're going to end up with magnetic field magnitude times 2 pi r, and little r here because we can vary little r. We can make little r go all the way to 0. We can make little r go all the way up to big R. If we make little r go beyond big R, we have to treat this problem slightly differently on the right-hand side of the equation. So on the right-hand side, we have mu 0 integral of j dot dA. J is uniform though, so it is constant. But as we increase the size of our loop, we have more current flowing through that loop. Okay, so how do we make it work over here on the right-hand side? Well, since J is constant and dA and J will be in the same direction, right? So J is in that direction. The dA vector will be in that direction as well for the orientation of our loop here. If we chose the loop to go in the opposite direction of B, then the dA vector would be pointing downward. That would have to be true by a right-handed coordinate system. So what we end up with here is integral of j dA, but J is constant. It is a uniform current density. So we end up with mu 0 J integral of dA. And what is A for this, this circular path here? Well, it's just the area of the disk inside that circular path. So mu 0 J pi r squared for the area. And then we can see cancellation of 1 power of r, right? So if we move everything to the other side, B equals mu 0 J, pi's cancel, 1 power of r cancels, and we're left with a 2 in the denominator. So linear with respect to r, right? So mu 0 J r over 2. Okay. How would we figure out what J is? Well, we're told that the total amount of current that flows is 3 amps. So what's the size of our wire? Well, our wire has radius r right here. So if we wanted to know what J is numerically, we would just take 3 amps and divide it by pi big R squared, but we're not even being asked to do that, so we don't need to do that. We're being asked, in fact, when is the field strength going to be equal to 36% of the field strength at the surface of the wire? And the only thing over here on the right-hand side that can change is R. So R is the only thing that isn't constant. J is constant here. J, it's a uniform current. So R can be reduced to 0.36 R. So we can make R go to 0.36 of big R, and then we would have 36% of the total magnetic field. So A is the correct answer, and we'll be back with the next question for chapter 29. All right, we're here with chapter 29 question. A uniform magnetic field is applied perpendicular to the plane of a 60-turn circular coil with a radius of 6 centimeters and a resistance of 0.60 ohms. If the magnetic field increases uniformly from 0.2 Tesla to 1.8 Tesla in 0.20 seconds, what is the magnitude of the EMF induced in the coil? And so I'll give you some time to work on that one on your own. If you're watching on YouTube, pause the video now and give that a shot. We'll be back in just a minute. Okay, I almost forgot to actually include some formulas here that might show up on a formula sheet, right? Which you'll be given on the final. So um, here we have a magnetic field increasing uniformly, and we're being asked about induced EMF. Well, that screams Faraday's law to me. So minus N d phi m dt, right? And also probably, excuse me, if the wire is being, if it's told to us that the wire has a certain radius and a certain resistance, then maybe we want to know the magnetic field of a coil of wire, mu 0 n times I, where n is the turn density, so number of turns per unit length. And maybe we also want to know Ohm's law, perhaps, so delta V equals I times R. So maybe our first initial impression is that maybe all these formulas might be useful for us in this question. I'll let you determine which ones are actually useful. Oh, one more, magnetic flux. So magnetic flux you can always write as an integral of B dot dA here. Okay, so I'll let you work on that one. Pause the video now and give that a shot. Oh, whoops. Okay, so on question here from chapter 29, we agree the answer should be B, 5.4 volts. The way to get that is to use Faraday's law, and we're looking for the magnitude, so we can drop the minus sign. And we don't have a continuous change here, so we can replace derivatives with deltas. It looks something like this. The area of the loops of the coil here are not changing, so we can write delta B over delta T instead of delta phi over delta T, and then the A just kind of pulls out there from the deltas or from the derivative, if you will. And plugging in the numbers here for what we're given using pi r squared here with the radius of 6 centimeters. For our magnetic field here, we have 0.20 Tesla initially, so 1.8 Tesla minus the 0.2 Tesla, so 1.6 divided by the 0.2 seconds here for delta T. We have 60 turns, so 1.8. Let's write some of this down just to have it all here. Minus 0.2 divided by 0.2. And then times the area, which is going to be pi 0.06 meters. That's going to be squared. And if you crunch the numbers on this, you're going to end up with roughly 5.4 volts, which is the correct answer there. Okay, we'll be back with a question from chapter 30 in just a second. Okay, here we are with a question from chapter 30. A 96 millihenry solenoid inductor is wound on a form 0.80 meters in length and 0.10 meters in diameter. A coil is tightly wound around the solenoid at its center. The coil's resistance is 9.9 ohms. The mutual inductance of the coil and solenoid is 31 microhenries. At a given instant, the current in the solenoid is 540 milliamps and is decreasing at the rate of 2.5 amps per second. At the given instant, what is the magnitude of the induced current in the coil? So I have a couple options: 7.8 microamps, 6.3 microamps, 9.4 microamps, 11 microamps, and 13 microamps. So this is a question where all the answers are kind of in the same ballpark, right? So we want to make sure that we're not rounding prematurely. We want to keep all our calculations as is and round at the end to the appropriate number of sig figs, which in this case is 2. Okay, so go ahead and work on that one. Pause the video, work on that one by yourself, and we'll be back shortly with the answer and discussion. Again, I forgot to give you guys some formulas, so let me go ahead and give you the self-inductance of an inductor, mu 0 n squared A times L. And perhaps we would maybe want to use Ohm's law here, and maybe we'd want to use Faraday's law, or maybe the inductor form of Faraday's law. So potentially many options here. This is also equal to minus L di dt here as well. So a couple different formulas here that might be relevant that you might think you might want to use, so you'll have to decide which ones are useful and which ones are not useful. Okay, good luck on this one. We'll be back in just a second. Okay, so we discussed it and we actually annotated here in the video a little bit. So what we needed to do here was simply apply the Faraday's law for the case of an inductor here, or two inductors with a mutual inductance. So replace L with M. And we're given the rate of change of the current with respect to time. So we can plug in the mutual inductance, the rate of change of the current. We get about 77.5 microvolts in magnitude there. And then apply Ohm's law for that coil. So the induced current is, the induced voltage in that secondary coil is 77.5 microvolts. The resistance in that secondary coil is 9.9 ohms. And so we apply Ohm's law to get the current about 7.8 microamps. We'll be back in just a second with the question for chapter 31. Okay, we're back with our final question for the review session. So I tried to choose one that would require a little bit more thinking here. Looks simple though. For an RLC AC circuit, the RMS current is 10 amps. If the impedance is 12 kiloohms, when the voltage leads the current by 39 degrees, find the average power of the circuit. There are options here: 930 kilowatts, 47 kilowatts, 93 kilowatts, 190 kilowatts. Let's give you some time to work on that one. Pause the video, or let's talk about perhaps some formulas here. So some things that might be relevant here. Maybe I see the word impedance. So impedance is square root of resistance squared minus the reactance of the inductor plus the reactance of the inductor minus the reactance of the capacitor squared. We can take a square root here on that. We're told that voltage leads the current, so maybe we want to remember Eli the Iceman, right? Eli the Iceman tells us about voltage leading current, or current leading voltage for which elements here. Maybe that's relevant. Maybe we want to remember that the max or amplitude values are equal to the square root of 2 times the RMS values. So this will show up on a formula sheet. Maybe we want to get ourselves a picture of what an AC series RLC circuit looks like. Something like this, right? Maybe we want to remind ourselves what the reactance of an inductor is. So omega L, reactance of a capacitor, 1 over omega C. And I'll leave it at that. There may be, for example, well, power first. So power average, if we use RMS values, we know it's IRMS, VRMS, and that would be the voltage on the resistor there. And that would get us average power. If we use the maximum amplitudes, it would be current through the resistor times the voltage of the resistor divided by a factor of 2. And there are other various formulas which may be useful here as well. I'll ask you guys what formulas you used when we go through the discussion here. But if you're watching on YouTube, feel free to open up your notes and find any other formulas you think might be relevant for this, and work this one out, and we'll discuss in just a second. Okay, so we came to answer A, which is the correct answer here. The way we do that is we get the RMS voltage here from the RMS current. So VRMS is I RMS times the impedance. This value comes out to 120 volts RMS, so just kind of like your wall outlet at home if you're in the US. So 120 volts RMS with a 10 amp current RMS. So power is I RMS V RMS, but we need to account for the phase angle here. So the phase angle, when it's not 0 degrees, in other words, resonance, multiplies in as a cosine of the phase angle here. And if you remember, this right here is actually the voltage on the resistor RMS. So it's only the resistor that dissipates power, right? The average power output of the capacitor and the inductor are both 0 because in one part of the phase they're absorbing, and on the other phase they're supplying, right? So, excuse me, on one half of the period they're supplying, and one half of the period they're absorbing power. So I did make a small little mistake here. This is actually kilovolts here. Thanks to one of my students for reminding me there. So 120 kilovolts because the impedance is 12 kilo ohms. And we can just go ahead and plug everything in at this stage. So we have 10 amps RMS. We have 120 kilovolts RMS. And we have cosine of 39 degrees. I don't know it off the top of my head. But when we crunch these numbers here, we end up with 930 kilowatts. Okay. This completes the final review session. We've now done 2 problems from every chapter, chapters 21 through 31. And that completes the review. So everybody watch the videos and go back through the videos multiple times on areas that you're weak. And maybe if you need even more practice than what's shown in the videos, you can even maybe try to alter the questions a little bit and try them again. Maybe change the wording of the question and think, okay, so now what would the answer be, right? Or maybe even just change some numbers, although just changing the calculations usually is not great for practice. Okay, that's going to be it. So see you guys on the final exam.